Curious, we take for granted that the device playing this video fits in your pocket. But in the 1940s, processing even simple equations required buildings the size of warehouses. Early computers relied on vacuum tubes, glass bulbs that controlled electrical current. They occupied massive amounts of space and consumed enormous amounts of power just to function. And that power came with a fatal flaw: heat. If you wanted to build a more capable computer, you had to add more tubes. But scale that up, and the resulting temperatures would melt the machine from the inside out until the glass shatters completely. The physical hardware itself was the ultimate bottleneck. That physical barrier stood stubbornly until 1947, when scientists developed the transistor. By replacing fragile, hot glass with tiny pieces of solid semiconductor material, they created a solid-state switch that ran cool and occupied a fraction of the space. This immediate miniaturization became a strict requirement for leaving the planet. By 1958, compact, reliable computing allowed NASA to perform the complex, on-the-fly navigational math required to launch the Explorer-1 satellite into orbit. Solving the physical constraints of heat and space was the mandatory first step. The solid-state transistor broke that thermal ceiling, allowing us to attempt advanced digital logic systems. By 1958, engineers realized they didn't have to wire individual transistors together by hand. They began printing multiple transistors onto a single module, creating the integrated circuit, which rapidly automated industrial and military equipment. Then came the microprocessor in the 1970s. Intel arranged millions of microscopic transistors into specific functional units, primarily the arithmetic logic unit. This acted as a centralized digital brain, continuously performing high-speed binary math on a single piece of pure silicon. This graph illustrates Moore's law in action. As the physical size of the transistor drops towards zero at the atomic level, the processing power of the chip curves sharply upward, doubling roughly every 2 years. Because the hardware was shrinking exponentially, the price dropped along with it. Computing components finally left massive government labs and entered the consumer market, starting with hobbyist kits assembled in wooden boxes. Soon after, that hobbyist culture matured into mass production. By the early 1980s, standardized personal desktops equipped with dedicated monitors and keyboards found their way into offices and homes around the world. We had successfully built millions of highly capable, miniaturized digital brains, but they were entirely isolated. A computer sitting on a desk in New York had no physical or logical way to share its data with a machine in London. In the 1990s, the engineering focus shifted from soldering hardware to writing software. We began developing robust operating systems capable of executing complex mathematical algorithms and hosting entirely new application languages. To support these heavier operating systems, data storage had to evolve. We abandoned tiny magnetic floppy disks that held only a few megabytes and developed high-capacity hard drives that could handle the massive files modern software required. With local machines upgraded, engineers established TCP/IP. These strict communication protocols forced completely independent operating systems to speak a common language, finally allowing computers to route information across vast distances. Once that network, the World Wide Web, was established, human behavior adapted immediately. Universities, scientific research centers, and industrial sectors started frantically scanning and typing decades of physical, historical data into digital servers. The pairing of massive local storage and global networking effectively built a permanent, universally accessible library of human knowledge. Then the connection went mobile. After the year 2000, manufacturers started sliding GPRS chips into standard voice-calling cell phones, bringing basic internet access directly into handheld devices. The tipping point arrived in 2007. The launch of the modern smartphone successfully placed a multimedia-capable, constantly connected node into the pockets of billions of people. This hardware ubiquity collided with the rise of social media to trigger a petabyte avalanche. For the first time, complex human emotions, social interactions, consumer reactions, and behavioral patterns were converted directly into trackable, stored digital metrics. Consumer laptops and phones simply couldn't hold that volume of information. The tech industry solved this bottleneck with cloud computing, offloading the storage and processing burden from local hardware to centralized servers. These vast data centers serve as the physical infrastructure for the cloud, processing the sum total of modern global interactions every second of the day. By relying on cloud infrastructure for convenience, humanity inadvertently built a centralized, interconnected nervous system, and that massive, unified data pool was the exact prerequisite needed for advanced automated analytics. Today, we have pushed the physical limits of hardware to the absolute edge. Semiconductor fabrication has reached the 2-nanometer scale, meaning we are now organizing processing power at the atomic level. To make sense of the cloud's vast data ocean, engineers designed machine learning. Instead of relying on explicit, line-by-line human programming, this software architecture is built to ingest chaotic raw information and independently find the structure within it. The engine digests the digitized historical records, art, culture, and behavioral metrics we spent the last 30 years uploading. By scanning billions of these interconnected nodes, it independently identifies the underlying patterns in how human logic actually operates. Once the system maps the history of our decisions, it can calculate probabilities. When asked a question, it doesn't search for a pre-written response. It predicts the optimal sequence of information to generate a highly accurate, original answer. This moves the technology past basic computation. A calculator executes exactly what you tell it to do. Artificial intelligence generates conclusions you never explicitly taught it to find. You can see the weight of this capability right now in the modern banking sector. Financial institutions are completely restructuring their operations around these analytical engines. By feeding an AI the institution's entire petabyte-scale transaction history, the system can execute continuous, automated audits. It flags microscopic anomalies and detects fraudulent spending patterns the instant they occur, without waiting for a human analyst. Beyond security, banks now use the behavioral data profiles established during the smartphone boom. By understanding a client's spending habits and reactions, the software delivers highly personalized, predictive financial advice instantly at scale. We have traveled exactly 80 years from towering glass tubes struggling to perform basic math without catching fire, to microscopic atomic-scale processors actively simulating the complexity of human thought. Shrinking computer hardware provided the processing density required to transform raw human history into a training ground for synthetic intelligence.